and so this has a cost, and this of course will have an impact on the structure of these networks. If you don't have any constraints for the web, for example, you have sites connected with hyperlinks. Basically, this costs nothing. To point from your website to another website, this costs you nothing. Which also explains why you can have an degree which is so large. I mean, you can have millions of sites pointing to the Google or whatever CNN website. That costs nothing. Here, for the road network, you have some spatial constraints. So you cannot have an intersection with hundreds of roads. There's not enough space. So all these let's say, transportation networks, which are really embedded in space, are in fact very different from what the usual complex network, which live in some abstract space where you can have a huge number of connections. So another example, the US power grid. We talked a little bit about some years ago, there was this huge blackout on the East Coast, which is still not yet completely understood. There's also, and this will be even more important with the German guys going out of nuclear energy, the transporting gas. So basically this will be a very important network for us soon, because the gas now will come from Russia to Germany, and then from Germany probably to France and maybe to Spain. So this is also a very important network, and its resilience. I never heard about the problem actually on the pipeline network. I don't know how resilient is that.
When someone cuts it,
it happens, yes. I think in Georgia also.
In Ukraine.
Yes, but now they avoid Ukraine. Yes, the point is that. but honestly, Russia the gas will arrive in Germany through north, I think, and will avoid Ukraine. They're aware of this problem.
It was in the news today that they started this pipe through the Baltic Sea.
Yes.
So I didn't see any studies actually about the resilience, and there's certainly on the more engineer technical side there are probably many studies, but the structure of this network, I didn't see any study about that, but that would probably be an important network. So now, transportation network, I will go a little bit fast, of course, the air travel network. So this is a little bit, I was talking about this network embedded in space. The air travel network, there are many ways to define it, actually. The nodes are very physical. The nodes are airports. But then, how do you decide that two airports are connected? So the usual choice, but you can choose something else, is that two airports are connected if there is at least one direct flight from one airport to the other one, which makes sense. But you could define, for example, some kind of route network, taking any convention if two airports can be connected, if you can go from one to the other in less than 2 or 3 segments, for example, things like that. I mean, there are many different ways to define this network. But this is, of course, an important one, and was actually, and is the main reason for the spread of diseases like the flu that we have every year, and will be the main carrier of diseases in the future or well absent. And this is the only way for a disease to spread around the globe in less than 1 or 2 days. So it's a very important network. But the links are, space is obviously important, but it's not a planar network. So it's a little bit different, its structure is a little bit different. Train, also, yes, this is the train network in Europe. So you see you have a nice example of a planar network. Then you can even study some, let's say, mobility network or construct, let's say. So we did this once in Sardinia. So you look at the flow between cities. So it's almost a complete, so topology is almost trivial of this graph. All the nodes are connected, but what is changing are the flow of individuals going from one place to the other one. And this, again, is very important for understanding the spread of disease and things like that. So, even at a smaller scale, here this is the road network. We would like to understand the evolution in time, for example, of this network. And as I said in the introduction, this is, how can I say, the road network is not enough to describe a city, what happens in a city, but it's a very important part of it. Sometimes it's an abstract of what is going on in the city, because it's the main let me say, way to go from one place to the other one, and basically to link the production location to the consumption location, which is the main goal of, main purpose of the city from an economical point of view. And of course, you can go in the city by walk, by car, and of course subways are very important. This is the Tokyo one, and with this very characteristic circular line, the Yamanote line, and this is a very important transportation mode. And as I will show you, most of the big cities have a well-developed subway system. So it's really becoming something extremely common, which is the art of movement and mobility in urban system. So after this little example, let's go to some more detailed question. So there are many problems, in fact, about when you think about these networks, think about the subway or the roads. What can we measure? What are the stylized facts that the model could reproduce? This is an important question, and so far it's not really, there's no real answer. It's relatively unclear what we would like. If you propose me a model of evolution of roads, it's still unclear how to compare it to the real world, actually, because we don't know exactly what to measure and things like that. Principles are not that easy also are they, first of all, are all these networks, because they are transportation networks, similar? Or the fact that you want to transport something from one point to the other one in space, is it enough to claim or to, let's say, to pretend that there is a common principle of formation? It's unclear too. There are many questions that we would ask, actually. The problem, as I said, the first problem is to get the data. So actually, this is why all these questions and others are not answered yet, is that it's easy now to get data about the network. It's difficult to get data about time-evolving networks. It's, if you think about roads or cities, or you can have a snapshot at a given time, but evolving in time, that's more difficult to get. But it's starting now. We are in an exciting time where GIS methods and things like that, we have more and more data. So we are really at the beginning of describing quantitatively the evolution of all these systems. So that's a very nice period. There's a big problem in these, in actually most of these networks, is that we are thinking in terms, especially for physicists, in terms of emergence and self-organized system where you have little agents doing their thing like they want, and in the end you see some collective behavior at a large scale. For this type of network, it's unclear. Sometimes the guys decide to build a big road there or there. So there's really this interplay between top-down and bottom-up processes that may prevent you from a simple model. Think about I don't know, a crazy thing. I want to make a model of Paris, the evolution of roads in Paris. In 1850, the Baron Haussmann came and said, okay, it's a big mess, and for many reasons created these huge avenues to go out of Paris and to reduce the congestion. Is this something that you have to put outside, and is it some exogenous thing that you have to add top in your model, or is it some emergent process? It's relatively unclear, and people are really fighting on this. Is a model possible, or do we have to add some extra intervention of coming in the model? That's very unclear. But just to use the next 5 minutes, these are not real new problems. Actually, you can find in nice books about quantitative geography, and in the 60s it was the beginning of this, what was called quantitative geography, so people really wanting to make some quantitative measures about geographical problem, which deals about individuals, location, basically space, flows, individuals. And this is, in 63, so this is a little model which was proposed by these guys, and you have seaports So I will not enter details, but this is the sea. So you have the seaports, and so that you have roads going to these ports, and some of them get bigger, and if they get bigger, then the roads become bigger also. So there's this interaction between the activity of a node and the importance of the road. So they were playing with little models like that. Idea was nice, but it wouldn't go very far. But in some cases, they even compared to reality. For example, this is a little model of evolution of the Sicilian road network in the 60s. It's interesting to see. So it's a very small network, of course, and so there's a complicated. This is creating a link. In fact, it's called link allocation problem. So you can imagine different reasons to put a link for some economical traffic reasons, depending on the node and things like that. But you see that in the end, this is the real network at that time, and this is more or less what they could infer with some strange stochastic model. But in the 60s already, that was not bad, and they were even trying to do some Monte Carlo simulation. So now it looks a little bit strange, but still, for this is 65. So it's something like almost 50 years ago. And this is a little model of stochastic evolution for a road network. So of course at this point the network was very small, there was no real comparison with experiments and things like, with empirical data and stuff like that, but still it was already in the 60s they were thinking of let's use a stochastic model and let's try to see what happens. And at least for me, it was a surprise to me actually. I didn't expect that in the 60s they were doing Monte Carlo simulation on the evolution of networks, which is the fact. It looks like a very modern title already. And here again, I will not enter the detail of this is for railway, and same thing on the left, the actual growth of the network at this in Sweden, and some simulated growth. So there are many. I will comment on that a little bit later. But of course there are many problems. The network are very small and so on, and there are many parameters and many specific considerations. So actually, as physicists, we wouldn't be extremely happy with these models because they're far too specific. So it's a little bit difficult to believe them. But until recently, so it's a long tradition, there was this little model about the Boston rail network. So this is the real one, and this is the simulation. But there is a trick here: is that the location of the nodes are given. It's an easier thing once I give you the location of the nodes. It's easy. Actually, it was a local optimization process. You connect to the nearest one by some rule. So it's not such a big surprise. The complicated thing is, of course, to find both the node location, and that's the complicated thing. Once I gave you the... But still it continues. There's some more... This is for the railway network. This was in 2006. I participated to this, and we proposed a little model also based on local optimization for the road network growth. So here are different stages. So you see the network growing. So you add more and more, let's say, nodes in some sense, and this creates the roads, and you end up with something which is not, which we could compare actually to empirical measure, because there are some empirical measures on road network, in particular in German cities and world cities on certain aspects. And so actually this little model, this is not the point here, but reasonably agrees with what was measured. So just to tell you, it's a long story, so it's not a new thing. So what has changed? Just briefly, so I think that we have more data now, as I was saying, and we have better computer, of course, but we also know much better networks. And we have this idea, maybe, that, in my point of view, that's the added value of physics to other fields, is that maybe we have a sense of important parameters versus detail. In the end, a good model, even in physics, is a model where you understand the dominant processes, and keep the smallest number of parameters. But we know that there are many things, many parameters, and so on. So maybe a good physicist doing a good model is maybe this. Able to extract the important parameters, the important mechanism, and that's maybe I believe that's this training in physics which could help us go in other fields. Engineers, for sure, they don't have this training. They will put all possible details in the model and try to reproduce what they observe. So I think this knowledge, this habit of modeling with some minimal number of parameters is a helpful thing, and this is definitely not what they had in mind in the 60s. So let me now, so before doing models and theory and stuff, we have to measure. So I'm going now to the second part, after this little introduction, and about the time evolution of subway systems in different parts of the world. This is work I did with Mike Batty, Camille Roth, and Sun Kong. And again, I like to remind that this is not a new problem but this is a source which is impossible to get. Actually, this is a master thesis in '67, so I got only this figure, but I never got the paper. So it's impossible to get. Anyway, but you see here, it's some kind, so it's done, I guess, by hand, you know, and it's a nice thing, and these are the different stages in the evolution of the London Underground Rail Network. It's very clear that it's difficult to say something quantitative on this. I didn't see the paper, but I don't expect unbelievable measures. So why subway? So there is a justification. Here is a simple number. This is the simple plot. So this is the fraction of cities. This is population, and here the fraction of cities with a subway system. And you see that basically, so there's a little fit. You can fit by this exponential. It gives you this value actually, and which tells you, so the cutoff is typical of a few millions, which means that for a city more than 1 million inhabitants, it has a subway system anywhere in the world. So you see that even starting from 5 million, you have 80% of the world cities which have a subway system. So it's something which is really, I say, universal, in some sense that you see everywhere, which justify its importance. So let's start with some basic static properties. So here's the list of so we studied basically the 12, approximately a dozen networks, the largest one in the world. So they all have more than 100 stations. So you have here the different cities. So Madrid is in it. Madrid is a very large network with more than 200 stations. So you see that all these networks, which are big networks, they are older networks, they have, let's say, order 10 lines, 200, I mean, from 100 to the largest one in number of stations is New York City. And you can make some simple measures first. And one is the average spacing between nodes, between stations. So I should say, yes, the nodes are the station, and there's a link when there's so this is the physical network in some sense. The segments are really the railway between the two nodes. And the shortest, I think, is Paris. Paris has an average distance between stations of 600 meters. And of course, I would say. And very naturally, the largest one is in Asia. I think Seoul, yes, has more than 1 kilometer. But I guess Shanghai, yes, is 1.5. But of course, you can understand this because these are the fastest evolving networks. And they need to cover a large space, so they're not going to be very dense and things like that. This is one thing. This is the total length of the network. It's not very interesting, but what you can do is that you can compare the total length to the total length of the equivalent almost regular lattice with the same spacing. So it's just, you can just, I don't know, if you have, let's imagine that you have a density of nodes, which is the number of nodes over the area. So then the internode spacing is given basically by 1 over square root rho, because this tells you that on average, on a little disk of radius L1, you have one node. So the total length is actually the number of links, and the number of links is basically the number of nodes times the average degree over 2. There's a factor 2 times L1. And this scales L1, so this is square root of A over N. And so this scales actually like as the area of your city, AN. So, and there's a prefactor. So this is the total length of your network for, let's say, for a typical regular, almost regular lattice, where you have a density of node N. It's a very simple calculation. And so imagine your nodes are randomly distributed and you connect to the nearest neighbor. And the total length is given by this one. And actually, if you look this for the road network, it works very well. You have this nice scaling with a square root N, it works very well. But here it's something else, and so you can compare the actual length to this, let's say, regular lattice length. And you see that you have some networks with relatively small values, like New York City or Tokyo, of order 0.1, and it goes to maximum, I think, is Osaka. And what does it mean? It just means that, I will show you some pictures, but this is a very reticulated one. It's very close to some regular network, Osaka. While this is the first sign, a small value of a large heterogeneity. You have shorter links, longer links, meaning that the distribution of this interstation is not peaked. In fact, this argument works if the distribution of interstation length is peaked with a very small variance, small dispersion. And indeed, so let me show you. So Paris, so these are the maps. Paris has a small value, but indeed you have some, you know, the center, as you can expect, has some, you know, you have some kind of almost regular lattice-like behavior, while here you have some longer links and things like that. You can compare to, it will maybe be clear, Osaka, for example, is still a smaller network, but this is really, you know, you have the main part, which is what the center of the city here, is really lattice-like. So this is what this, yes?
How do you measure the area? Because that's a little bit tricky, right?
Ah, yes, the area, yes, you have to...
Because if you have a line that is very...
Yes, these numbers are subject to some error bars. Of course, you have to take the area which is consistent, I mean, you have to take the good definition consistent with the network. I mean, some networks, for example, Paris almost stopped, not in the middle, the subway of Paris stops almost in the center of the city, and what we call Paris, inside this ring, the peripheric. What is going out is not very, very important. In some other cases, you have to take the metropolitan area, the whole urban area. So it can be tricky.
These kind of features are just cartoons.
Yes, absolutely. Yes, I will show the physical.
It doesn't mean that it's really on a grid.
No, but it's still relatively reasonable. I will show you the. So here are the it's a good image. I will show you. Moscow also is. Moscow is very strange, but as we see, Moscow has been planned. This is an example of top-down process. It's not something emergent in the communist country. Apparently, they decided to construct some stuff, and indeed, what we'll see in all the plots, Moscow is always a little bit out of the usual statistics. But I think it's not really emerging. I mean, there's a big difference if everything is planned by some group of people, or if something results from the interaction between users and planners. So I guess that's an explanation. But your remark was absolutely correct. What we see, what I show here, in most cases, is relatively, you can trust this image. In some cases not. For example, this is the real spatial network of Moscow that you can compare to, for example, here, maybe we see a little bit better. This is the design image of the map, and this is the real one. This is, in general, you are right. When you have the metro map, don't believe that it's the geographical image. That's for sure. That's for sure. It can be extremely misleading, in particular for Berlin, I think. It's a big mess. This is Paris, for example. So So and so indeed Paris, you know, when you see the metro map, it's very, very different. Maybe this might be London. So in all the study we did, of course, the data correspond to the geospatial data. And of course, we didn't use the real spatial map and not the representation. And it's interesting to see, by the way, that the representation of map is converging in all the parts of the world. We are doing the same map of the subway, and there is this kind of design rule that the angles are 45 degrees only. So you have only these simplified lines and things like that. That's a very interesting thing to see. So if it works, some dynamics. So it's so these are just simple static things. It's not really what I'm interested in here. I'm more interested in the dynamics. Unfortunately, it goes a little bit fast. Let's see if it works or not. Does it work? It goes a little bit fast. Sorry about that. But from the beginning, 90-something, Berlin is a little bit bizarre, but it's difficult to understand something. Paris, here, if you see something. So again, there's this idea that at a certain point, very fast, the core, unfortunately it's going far too fast, the core is there, then the branching are exploding. So there are different processes, and you can have a first feeling of these networks, which is that you have a core region plus some branches. And this indeed is a very simple general structure. I can show you others, but I'm not sure it's very, very informative. So here, so this is a very old one actually, from the 19th century to now. So in this case, very early, there are some very long filaments. and then what is usual is that first the core is getting denser and denser, and at a certain point the branches are growing.
So when you compute the area, you use the area?
No, the area is given by some other data set. The area is the area of the total city. It's not the area of network. I don't know how to define the area of network. So I have a city, and I have the points in it. That's the area. So it's the area of the urban system, of the city.
There are many parts of the city which do not have metro. Large areas, if you look at the London before, there are large empty spaces there.
Yes, no, of course, it's a, let's say, back of the envelope argument. It's a number, I mean, this is not a number you can trust absolutely, because the area is difficult to, and moreover, this argument assumes something, is that you have a uniform density, which is not true in many cases. But it gives a first, first idea of what is, or you can compare your network with something which should be some regular lattice. It's the first grasp of the network. But I agree with you, area is a complicated thing. So if you look, you can compute some simple things about the dynamics. So here are just some little numbers that you can compute easily. So this is the initial date of these huge networks. So you see that the oldest one is New York. Then in Western Europe, of course, in Paris, Tokyo also, but because a rich Japanese guy, actually sold the metro in New York, and found it so great that he decided that it would be nice to construct one in Tokyo. So this is why actually Tokyo started early to build one, and you can compute some simple thing. Here also, these are really some numbers to give you an idea. You can compute some average velocity of expansion. That's a number of stations built per year. So you have some numbers. So there are, of course, this is an average value. So of course, they are very small, these numbers, except for these crazy networks, which are Shanghai and Seoul, which are really, they are recent first. They started, Shanghai really started in 95. And they are expanding like crazy because they are already super huge network. So, on average, it's something like Shanghai is 15 stations per year. 15 stations per year, it's something like... of course, you can have large fluctuation, and in fact, you can have... This is... I'm not entering the detail because this is really history. You have fluctuations of activity depending on wars, on the money you have, and so on. So this is a very complicated thing, which is which is for the moment very far from physics.
Sorry, for the velocity you calculate the total age of the network? Or, I mean, because some
it's the average velocity, so you compute the number of stations per year and you average over a year. So I guess it's one measure. You could actually measure many things, so this is one possible measure. So on average, over all the duration of the existence of the network, for Shanghai, for example, you have 15 stations per year. Which could mean that you have 0 1 year and 30 another year.
A question, when they grow this network, do they optimize anything? For instance, the number of passengers that will be, when they build new station, how do they decide where?
If you have the clear answer to that, then you have a good model for the evolution of the network. It's a very complicated thing actually, because it's a matter of demand. Also, it's because you're not connecting in the vacuum. So you construct a new stations because there is some demand in the area. Some people need to connect to the network. So it's actually a complex economical process. You have the traffic effect, you have the population density effect. So this is why we started with the minimum thing, which are just measures, because so far there are no, I mean, again, in this business, the question of existence, the possibility of a simple model is unclear. Do we have to go like the engineers do, the civil engineers, and do the most complicated model with all possible details? Do we have to do that? Or can we extract something simpler with a small number of parameters? It's unclear, because economists will tell you, yes, there's the how much money will win, the spatial distribution of people and their income, and so on. You know, so it never ends. So the idea is to start with the simplest, and then maybe to add complications.
But what is the purpose? To understand how the network has been growing, or to design a better growth of the network?
No. The point is to understand how they grow.
You cannot change when it is done.
No, the point is a very let's be naive a little bit. Let's take all these networks. Let's see the time evolution. We will plot some quantities, and let's see if we can understand something. It's a very simple approach. It's the most pragmatic one, and we pretend, which is almost true, that we know nothing about economics and transportation economics. And we see. So anyway, what I wanted to show. Yeah, so there are many difficulties, of course, because it's not that easy. The nodes there in space, which is one more parameter to take into account. So it's a station network, as I was saying. And so you have always new station, new line. So these are time-evolving spatial networks. And for those of you who are working with networks, this is really something that we don't know very well. And in fact, because it's complicated, you cannot make one drawing. Usually these networks are relatively large. And how to visualize actually the evolution of a network is unclear. There's no clear way to do that. And moreover, it's maybe a little bit paradoxical. There are too many things to measure. So the good thing, so it's not completely easy to extract what to measure. For those who know network, the usual stuff, which is degree distribution, clustering, and so on, is completely irrelevant for these networks and spatial network in general. You don't have a scale-free distribution and so on. This is totally anecdotal. The clustering is always large because you are in space and so on. The diameter, you have spatial networks, so the average distance between two nodes always scales as since you have something which is lattice-like, in dimension d, the average shortest path scales like n to the power 1 over d, where d is the dimension, so here we're in dimension 2, so it's square root of n, which is a big world. You have to compare this with the log n of the small world thing. So these are really, from the complex network point of view, these networks are not super interesting. So you really have to focus a little bit on this spatially evolving network and time evolving network. And these are planar networks, okay, but there are many things to measure. So the solution that we found is actually to think about, to propose some templates that by inspection, I cannot say better, by inspection of this network, there's still something recurring, which is some kind of structure that they all have, and which is this one. And, basically, you can check actually that these big networks, they all have this kind of structure. And this is the one which will help us to devise some tools to measure, and what to measure. And in fact, when you think about, you always have, I mean, when you check these networks, you always have some core region, which is defined actually, which is the complementary part of the branches, actually. You check the branches, you always have branches which are not connected, and once you are not in the branches anymore, this is what you define as the core. And this is exactly what you see in most networks. And so this is, let's say, some template which just help us to tell us what to measure. Because that now we have this image here, we can easily define some quantities to measure. For example, the core, how dense is it? It is. It's a planar network, so there is a standard parameter that I will give, which tells you how dense is the network. The branches now, how long are they? What's the number of stages of branches compared to the total number of stations? And so you see that with this template, it took us some time, but questions are much more easy to ask, you know, and what's the velocity of evolution of branches and things like that. And actually, in the last part, this image can help you to understand how the network evolves, by which process it evolves. And in fact, the process is indeed, I can tell you now, growth of branches and then connection of inter-branches connection, and densification, growth of branches, and so on. But let me start with these parameters. So I was telling you, you can compute the average degree of this core region. This tells you how dense the central region is. And this is something which is actually related. It's what is called the alpha index for planar networks, is the number of cycle or phases, elementary cells, over the maximum number you can have for the planar network with the same number of nodes. So this is a standard index. So E is the number of edges and N the number of nodes. So this tells you how connected and how dense is the core. For branches, as I was telling you, that there are simple things to measure. And again, these quantities would not come naturally if you don't have this idea of branches and core in mind. If you think about some planar network, you know, it makes things complicated. Here, if you think about branches and core, you can count the number, what's the fraction of number of stations in branches. How much do they represent in terms of number of stations? And you can also add some spatial information, which is the average diameter of branches, in kilometers, let's say, over the average diameter of either the ring or the core station, which tells you what's the extension of the branches.
Simple question. Is this core related to like the k-coordinate networks? I mean, from your picture, it looks like it could be like a 2-coordinate, 3-coordinate. Maybe I'm drawing so many inferences from the picture.
I don't know. I think there should be some overlap because the terminal station are k equal 1, then you have the k equal 2 nodes, and then you have the big the circle. We didn't do it with the k core, but there should be a relation. Yes, indeed. Although, yeah. So actually, I spent too much time at the beginning. So let's see how they evolve in time. Here, so this the thick line is the average, and so you see all the cities. So what I was saying is that this triangle here, down triangle, is Moscow, the bad guy, and so you see that remarkably, in fact, the dispersion, I will figure the dispersion. There's a simple algorithm to define the core. You always have branches, you have the terminus station, you go along the branches, and once you are not on branches anymore, this is the core. So there's a non-ambiguous way for any network to define the branches and the core. So you do this. You make some measure, there's nothing to fit or whatever, and then you can measure the average degree, and you see that it's growing a little bit. Here the average value I think is 2.5. So it means that you have a mixture of 2 and 3s basically. 2 are the stations which are intermediate stations, and then probably you have 3 and 4, of course. And dispersion is relatively small, and most of the network behave in the same way. And it's of order 2.5. Now
what is the x-axis?
Oh yes, yes. Sorry, I should have said that. Good question. In fact, the first plot that we were doing were versus time, which in fact is not good because every network has its own, how can I say, rhythm. Depends on many things. So actually, we tried different parameters. Population was a priori a good thing, but a little bit complicated to implement. So finally, the good measure was the number of nodes. And this is basically the fraction up to, so our last data are 2009, I think. So this is the fraction of the number of nodes compared to 2009. And indeed, things, all the plots are much better if you plot versus the number of stations, which seems to be the natural measure. It's the size of the network, and that's the natural measure of the evolution of the network. And so this is the size of the branches. Again, you have this guy, at the top here is Moscow, and which has this very large branches. In fact, there is a factor 3, which means that the size of the branches here in Moscow are 3 times the size of the core. So there's really a will to go very, very far away. So in fact, in some sense, the function of the network in Moscow is also to bring people very far away to the center. This is a little bit different from a more denser network with smaller branches. But you see that the dispersion is not crazy. The average is of order 2. Actually, I think I have it here. Let me show first before the dispersion. So eta is the ratio of branches, and beta is the term. This one is the number of stations. This is the function of number of stations in branches. Dispersion is a little bit larger here. Again, Moscow has 60%, more than 70%. 70% of the nodes in the Moscow network are in branches, which is really crazy. I mean, in terms of the other network. So you have a dispersion, you have something about 40% and variation of plus minus 10%, which is not, I mean, we cannot claim that there's okay, it's a time evolution, so we have to wait a little bit more maybe, but it's maybe too early to claim for some universal pattern, but still there's something. These networks are not that different. If you look at the dispersion versus time for these different parameters, for the average degree of the core, dispersion seems to be relatively constant and small. Of order, this is the relative dispersion. So it's of order 0.1. So you have 10% variation, and it's much larger for these, for the size of the branches and the fraction of station of the branches. It's maybe too early to say that it's decreasing. It's going in the good way. We have to wait a little bit to see if these networks are converging to something which is the same thing. And now I will finish with something which maybe some of you know, because there's some fractal properties. Actually, there was an old paper, not that old, 91, by French guys at that time, Benguigui and Daou. They made a measure of the fractal dimension of the Paris subway network. This is the last property that we could check. So the question is simple. You take the center, which is basically the barycenter of all stations. By the way, it's interesting to note that the barycenter, the gravity center of all stations, corresponds very well to the center of the city and is stable for all these networks. That's an interesting thing. And
in Barcelona, this is not the case.
Barcelona, I have to check. I don't remember.
It will not be the case in many
No,
cities.
I think in Barcelona it is the case. Actually, there's only one network for which it is not the case. It's New York. Because New York, you have Manhattan, and then you have the Bronx, and this is crazy. The reality center. But Barcelona, no, the by center, the movement of by center,
It will depend on the position of the sea, rivers, and mountains.
Yes, no. What I mean is that in time, the Barry center, even when the network grows, stays stable. So this is really, I can show you. I have the plots for that. So anyway, you can count the number of stations in this disk of radius r. Okay, this is the usual thing for fractal things. And what they found at that time is that at a short scale, which is typically the size of the city, you find something like n of r going like r squared. So if you remember the fractal dimension, this exponent is the fractal dimension, is 2. Meaning that for up to a certain scale, you have some uniform density of nodes. It's just a fractal dimension. And then they had this strange exponent of 0.5, which they had many difficulties to explain. And what I will show you in the last minutes is that, in fact, we can understand this change of behavior with this simple template. And actually, this is easy to understand in terms of branches, of core and branches. So let me first... So first you can define easily the size of the core. It's just when you take the barycenter, you increase the size r, and when you get the number of nodes in the core, this defines the size of the core. And so this is really from the network. A priori, it has nothing to do with the city. But in fact, it does. And so I didn't check every values. I know that for Paris and Harvard and Tokyo, it's absolutely reasonable. It seems to correspond, this core seems to correspond to what we call the city center, let's say, or the core of the city. Even if this is, but this is a, let's say, purely quantitative characterization. I didn't put anything in it, I just find this number by looking at the networks and the location of nodes. And then in order to have something rescaled, you can plot n of r divided by this number of core versus the rescale parameter by this core. So you can compare all the cities with each other. And it gives you this plot. So this plot is interesting. So it's really like it's basically like the Benguigui DAO results. So these are for the different cities. So we indeed have a regime for R smaller than the core, which is, okay, there are fluctuations, but clearly the slope here is of order 2. So this corresponds well to the image of some points uniformly distributed in the core. Then you have some, at large R, you have some saturation, you know, but this is expected. If you go very far away, the number of stations doesn't change anymore. At a certain point, these networks are not infinite, so you have a finite size effect, and this is the saturation. And in some cases, you have some intermediate range. This is not always very clear. In Moscow, of course, it's not a good choice here because branches are very long. So, which means that the regime where you are out of the core and not at saturation is the biggest. And the size, in fact, of this intermediate regime will depend on this parameter which was eta, which is the ratio of the size of the branches over the size of the core. And in this case, in Moscow, here you have this little regime, intermediate regime here, with, I'm not claiming anything about this value, but the slope here is of order 1, if you want to see a slope. And how can we understand the things? So the natural explanation is that if you think about this template, this core plus bunches, the number, if you are below the core, then this is just a regular, you have a density, you have a core density, and you have a number which is just rho times the surface. So it's like r squared, a fractal dimension of 2. Now, if you are beyond the core, so what you see now, you see branches, and you're below saturation. So the number of nodes is what you see in the center, plus the number of branches times the length of the branches between R and RC divided by the interstation spacing. It's a very simple thing. Delta R, it could in principle depend on R, is the spacing between two stations at the distance R. And in fact, this is changing with R because usually the farther you are and the larger the spacing between stations. And so this is really a very simple formula that you would write down when you see the template. If you count the number, this is just the number of stations counted. And all this is consistent. Actually, if you look this delta, you look only the branches versus R, the plots are a little bit ugly, but basically for Moscow, you find something which is almost constant of order 0, which means that the interstation spacing of branches is constant, essentially. For Paris, it's really gross. So if you are close to the city, the spacing is still dense, and then it's less and less denser, and the branches, the distance between stations far away are larger. And if you think about the previous formula, if delta R is scaling like R to some power, then N, the number of stations that you see at a certain distance, is just scaling like R to the power 1 minus tau. And so this, if tau is basically 0, for Moscow it gives 1, which I showed you before. So of course the range is very small, so I will not bet my head on it, but it's consistent. And for Paris, actually you find 0.5, which is exactly what, which gives you an n of r to the power 0.5, which is the Benguigui-Daou result of 91. So we recover in this framework very naturally the fact that you have an exponent 0.5, which was a nightmare to explain in terms of fractals. Benguigui and Daou wrote some crazy stuff about what is happening, but you cannot really interpret 0.5 in terms of fractal dimension. It's complicated. Here, in terms of branch, you have a very natural result. So in this sense, it's a very nice confirmation, a natural explanation of this odd result. So let me conclude on this. So it seems that results seems to indicate that we have a convergence to the same structure. Actually, for sure, this template is relevant for all these networks. Even New York, you can define some core. It doesn't correspond to Manhattan, but you can define some core. You can always define it, actually. But apart from New York, which is a little bit strange, all these networks, they behave very nicely, and they have numbers. They are defined by numbers which are basically of the same order, that's for sure. We don't have different order of magnitudes. We have basically the same number. An average degree of the core, which is 2.5. The ratio, the extension of branches over the size of the core is over 2. So basically, for most of this network, the branches are twice as long. The distance from the center is the double of the size of the city center. So we have these simple numbers which are with a small dispersion. So I think we still need to wait 10 years or so to check that. But it seems that it seems that we got the pattern. And now, of course, there are different things to do. Basically did, but the paper is in preparation, is that now we have really to define all this growth. This is the next part. We understand that there is this general structure here with core and branches, but all this network, the little movies, fast movies that I showed you, how is it really going? So it seems that we really have this densification and growth of branches, and then inter-branches connection. This is how it seems to grow. And which is the path to a simple model, actually. So, and without economics, and of course this is a blasphemy for economists, because we didn't put any economics in it, and how can we make a model which reproduces most of the things? So how can I say? That prefigures some discussion with referees, which will be interesting. And so, because I must say, is maybe we won't be able, but so do we need for a good model of subway evolution to put the evolution of population density and activity density? You know, that's any economist or urban planner would say yes, very likely. Maybe not here. Importance of planning, I think we have an extreme case, which is Moscow, but and Shanghai in some respect. It's unclear too. It's unclear too that we cannot model with a simple mechanism the evolution of these networks. And now some other perspectives which are related a little bit. We are also finishing with an Italian group the evolution of the road network. So that's fun too, because what we understood with subways, of course the structure will not be the same, but maybe the dynamics will have something in common. And here too there's this problem that when the road networks evolve, do we have to put the population density in it or not? That's, I mean, all the economists, all the arguments that you can use against the modeling of subway network, you can use it on the road network. Actually, it seems that there are very simple things we studied. This is a nice thing. Almost over 200 years, the evolution of the road network. And then, this is a nice thing I'm starting, and just with Pablo Jensen, who is in Lyon, we have the data for the French railway network in the whole France, the evolution time of the whole network. And so it would be fun to try some modeling on this, and hopefully one day I'll come back to talk about that. And this is a crazy book, Marc Ovenden, and it's a book with only metro maps, all the metro maps in the world, and so this is a fun map, but it doesn't stop because it goes directly from Barcelona to Algiers. It doesn't stop in Palma, I checked. But you can go from Barcelona to, on the red line, maybe you can go to Paris, yes. And this is only all the maps on the subways and the history of all subways in this book, which is actually very nice. Thank you. Sorry for being
Marc, any questions? Is there any study of the structure of the network using time instead of distance? And for example, when two lines cross, it's very different. If you go in the same line without commuting, then you have to change. The distance is the same, but the time for the user is completely different. I don't know if this looking the same distance as time would be make a difference.
Yeah.
I don't know.
Actually, there are very few studies about the time evolution. There are some very historical things which are not quantitative, and there are few. Yes, you can measure this by some average. Let's say the number of changes, average number of changes to go from one point to the other one. Yes, there are 1 or 2 papers on this. Yes, to give you the reference, but they are very very short papers, and what is clear is that a model anyway for these networks would be a line, growth of line model, which is very different from what is usually done for networks, where you connect 2 points, or in the Barthelemy, you choose a rule to connect 2 points or not, or scale 3 or whatever. Here you have lines growing, which intersect, and sometimes it's nice to intersect, sometimes it's not nice to intersect. And indeed, in some cases, intersection is nice because you create a connection. In some other cases, you see, in Manhattan, it's crazy, you see parallel lines, which from an economical point of view sounds crazy, and they're very close. And this is complicated because a reasonable model would merge immediately, these 2 lines. But probably there are many things like that, yes. We have to think in terms of line, and this would be the basis of a model. And there are very few measurements.
Marc, imagine I am the mayor of Palma, and that the crisis is over, and that I have decided to grow the subway lines of Palma. What can I learn from what you have told us that could be useful for me?
No matter what you look, it's more of a point.
Actually, it's difficult to say because we are.
Yeah, I'm trying to understand in which way this can be.
Because we are actually, we were trying to discuss here, some sense, the long time limit of this network. So I don't know. So it seems, and it's not even super clear. It seems that there's some convergence to some, some kind of same limit. The short time evolution, the transient things, I really. From this study, I cannot say anything because I know what I know. I understand more or less about the big networks with many lines. Here we have 10 lines, at least 100 stations. So here you have what, one line?
I want to know it. So when you tell me whatever I do and the next measure of Palma will do, after many years I will get something like that.
Yes. Yes.
So decisions are not important.
Yeah. No, if you believe in this, yes. Yeah. Of course, there are some constraints because on one side you have the sea. So for example, the Chicago network is the lake. So developed in a very strange way because you have to avoid the sea. So evolve more quickly, in the lateral along the lake. And so this is a strong constraint. Yes, so I guess, yes, maybe you will. But basically to have a loop, at some point to have a loop, to have a larger core, a dense core, these are things that we see really everywhere. Yes?
I have two questions. One, I suppose that the similar principles apply for the bus transportation. I expect to have a core and then lines go into the outskirts. And the second is, what about, for example, in the metro in Madrid, you could have two cores, right? Big Madrid and, for example, I don't remember, but I think that you have some other lines.
Yeah.
That if two of these lines are connected, then the picture changes completely, right?
Yes.
That the description you are making, what is missing is. Still, if you believe the
algorithm is relatively clear here. You start from this, you raise this, and you get some.
No, this is the metro, but there is the light metro, and that is also connected. So what I'm saying is that at some point you could have a core in one side, a core in another side, and then connected. And then the picture about branches.
Yes, this I really don't know. First, for the bus thing, I'm not so sure because the constraints are very different. Here you have to build in a hard way. You have to for older cities. It's underground. You have to build stations, and this is very heavy and necessitates large investment. For bus, it's not. This depends on the road network, and I believe the route is something more virtual in some sense. It's a subset of the road network which exists. But you can decide any road, any stop. It doesn't cost you as much as really building a station stuff. So I think it's interesting to check the bus network. I'm pretty confident that it would be very different from the subway network, which would be closer to something like the train or light.
But that's very contradictory because you say it will be different because of an economic argument. And you said that economic arguments do not play a role.
No. What I mean is that there's it doesn't depend on there's things are probably more complicated, but the road network probably interacts with the subway network. But once it's given, you can choose the route, and this doesn't cost you anything. I think to answer you, we cannot completely ignore economical arguments, for sure. But it seems to me that it would be interesting to see the
the question is, you have analyzing the underground, you have seen that this is what you see. You have a core and the branches. Why you have a core and branches is probably not something that is mandatory to have it that way. So probably it's used as the concentration of people, the concentration of salt is also higher in the center and it decreases toward the outskill. So probably so it's not that you have no shown what is the explanation for that. You only have shown that this is what you see.
Yeah,
and probably there are economical reasons.
I agree, but the appearance, actually it's true for the road network. There's this nice thing that there's a ring which appears at a certain point in all cities, and also in biological systems, in fact. And this is clearly, well, to me, it's related to congestion. So it's clear that at a certain point, if you have a purely radial structure, at a certain point there will be huge congestion at the center. So then you create this ring which allows you to connect different parts of the network without having to go to the center. So there's a cost actually associated to going to the center, which becomes too high. And this at a certain point forces the system to create a ring. And actually we see that in all the cities. And the only thing that I don't know is how to make a simple model for this. You know, I would like to see something nice, which at a certain point, if you want to go, for example, if you want to go from ear to ear, in a purely radial structure, or let's say from ear to ear, in a purely radial structure, you have to go to the center and then go there, which means that at this point, the centrality or the traffic will be extremely large. Now, if you have something like a ring, you can avoid, and this is particularly true for cars, for example, you can avoid the center, so maybe it's a little bit longer, but in time it will be shorter, and the traffic will be less. And so in some sense, there's some quantity which is optimized here, which is the time spent or something like that, and which appears in all models. But I would love to see a model, even of roads or subway, which at a certain point produces as a solution, as a natural solution, a ring. So the question of the ring, I think, is interesting, but I understand it intuitively, but I don't have a simple model and a simple mechanism to explain it.
And why don't you have the engineer? Why they build the ring? Because at some point they have, at least in Madrid, they have probably 5 lines, and they decide the 6th one is a circular line. Why did they decide to do that?
The problem is that it's not for all cities, and it would be simple if it would be like that. Is that for Madrid, you're probably right. For Paris, for example, you don't have a line, which is a ring. So, you know, and the ring in this case is purely topological, it's the junction of all these things, but you don't have one single line, which is the ring. So I don't know exactly what it means, but you don't have the ring, it depends on how you define. A line which is ringy, let's say, it doesn't exist all the time. In Paris, it's relatively central. It's very close to the main line, but we don't have a nice ring. But it's true that, for example, in Paris, they recently, and it's still a big mess, they built a big tramway doing the ring on the boulevard extérieur, so really encircling Paris. So it seems to, for some reasons, there's a natural pressure at a certain point which pushes the engineer and the urban planner to say, okay, let's make a ring. But you're right.
Well, I think, for instance, the buses in Palma, they are all radial distributed. And
last year, 2 years ago, they made 2 rings.
Okay. I didn't know that, but some years ago it was so complicated. So anywhere you go, you have to take 2, go to the center and then turn around. That is very hard.
Yes, and I think the simple optimization. I think Neil Johnson made a little paper at a certain point, showed that it was a nice little paper. You put a cost. It's a ring, okay, and you put some random links, and you complete the shortest path, and there is the average shortest path. And if the cost going to the center is too large, then the average shortest path go along the ring and things like that. So it's a nice little paper, and I would love to see, it was a PRL 2 years ago or something like that. Ashton, Johnson. And I would like to see a little simple physicist-like model, let's say, explaining the appearance of these rings, you know, and to my knowledge, doesn't exist one.
A short question regarding the first quantitative figure that you showed, that was a histogram of cities indexed by the population, and then the probability that they have that one. I was totally surprised by that, because I was expecting to find something which was sigmoidal, so some real threshold in there. Because I heard many times this thing, this rule that, okay, for a city to be reasonable to have network should be bigger than 1 million and so. So
But this
therefore,
is-
I mean, it means that there are a lot of cities, or when you don't see a threshold there.
No, but this is this is the cumulative thing, right? It's for population larger.
Okay, sorry.
Population, sorry. Yes, for population larger than 5 millions, then 80% are of the cities have a subway system. It's the cumulative. For population super large, for cities with population larger than P, you have a percentage of these cities with population larger than P, which have a subway system. So it's
No, but probably he's meaning
So it's not the quality
the
distribution.
curve is not in, it's like this curve, for example, in populations, cities with a very small population, you have 4% of them have a metro, have a subway.
No,
the ones with zero population, well, zero probably means small. You have 4% of them have.
No, there's a small percentage, yes, because the pool, the set of cities that you consider is much larger. Okay, so one way to represent it, but still it means that if I'm interested, this is maybe why I plotted this way. But if I'm interested in cities larger with population larger than 5 million, let's say, I take a threshold 5 million. I look only the cities with population larger than 5 millions. It's a certain number. Then in this number, something like 80% have a subway system.
Including all the African cities and all the Asian cities.
Well, these are the world cities.
Okay.
Yes, yes.
These
are the world cities.
I was just surprised that 1/3 of the cities over 5 million people do not have a metro.
5 million?
Surprised. 1/3 of the cities.
Yes, well, I didn't do some geographical study, but
This cannot be cumulative, right? Because it goes down. So it cannot
well, it's really the percentage. So I didn't check the geography, but you have many cities of more than 5 million. I don't have the figure in mind here, but I have to check. But I was surprised by the opposite. I thought that it was a lot, but you have the. I don't know. I didn't check the geography. You have South America, you have Africa, you have many countries, undeveloped countries. You have India, many cities don't have a subway system. In China too, actually. China, cities with more than 5 million inhabitants, that's a lot. Unless I made a mistake. Okay, I have to really check, but I thought it was a lot.
Okay, so, well, there's no more questions. We start with